So this is a topological sorting, and like in our previous video we have to do this using the DFS code, but now here we have to using the BFS method. So like in my previous video I already explained like what's the meaning of this topological sort, so I don't do this again. So if you need the further explanation, so you have to see my previous video where I explain it the DFS method also there. So like see, since coming to this BFS part, in this we have to use our in degree method here. So like what's the in degree here? So it's nothing but since this is a directed graph, because topological sort is always valid for the DAG, directed acyclic graph there. So every of the node, either some node is pointing to it, or another possibility is it can point to other. Okay, so let's say if I'm talking about this node, so what are the if another of, or we can say out other nodes are pointing to it, so these nodes becoming the incoming forwards, so that means these are contributing to its in degree. Similarly, if it is pointing to somewhere some other node there, so that is referred as a, we can call it as a out degree there. Okay, so like here we have to see for the in degree. Since we also see in our previous DFS question there, like first of all what we do, we have to simply visit all over or simply explore all of our nodes, neighboring nodes there, and after it exploring, we have to simply push node in our whatever the data structure we are using. Since we are using a stack there, and I already explained what's the why the stack there. Okay, so here what's the intuition here, we have to process what are the nodes which has no incoming node, no incoming edges, or we can say we have to process the nodes with in degree 0 there. Okay, so like so why we do there, because we can say one thing, like whenever I have to say that there is a no in degree, so what is mean, so it's nothing but the, because if there's a no in degree, that means it has a no dependency. So what it means that this node come first in ordering. I mean it can be say it can come first in ordering. Okay, let's say if I'm taking this example here, this is a 2 3 4 1, since this is a directed, so make it as a directed there. Okay, so this is the directed part, like calling for this, there's an in degree for it 0, it says in degree as a 1, it has also in degree 1, it has also in degree 1. Okay, so among these all of the nodes, it has in degree 0, so that means if I'm write the topological sort, if write the any of the topological sort, it should come at the first position. Okay, because there's no any other nodes that is pointing to it, it means it has to starting. So what we can say, so whoever the nodes are having the in degree as a 0, we simply have to process them as a first priority, we can say. Okay, so like let's say if I'm taking this example there, so again we have to see its in degree is a 0, its in degree is a 1, it's 1, it's 1. Okay, so now we can see like why we have to start, so that's why we can say let's just summarize this part here, like we have to process with no in degree no in degree nodes there. Okay, so now coming, so what's the key behind this? First of all, we have to calculate what is the in degree here. Now what we can do, we have to simply push what are all of the nodes with, we can say in our in degree is such that it is nothing but the 0. Okay, into what we have to data structure we are using since this is a BFS, so that's why we are using the queue. And like for BFS code, we are using any of the, like it takes a recursion stack, or either depending on the question we can also take an external stack there. Okay, now how is our BFS code is running there, so it is running as what we can do here, simply we have to pop out of the node what is the front node we have in our queue there, we simply add this to our answer there. Okay, because that is adding or that is adding to our main resultant vector there. now what we can do, since this is popped, means let's say if I'm starting from this, I have to insert this in our queue. When I'm popping about this from our queue, so it means, let's say we have to remove this part. So if this is removing, so it means this edge is also treated as a removing. So that means it's in degree, initially it's in degree as a 1, but now it's in degree reduces to 0. Okay, so that's mean what we can do, we have to reduce in degree of, we can say, the neighboring nodes there. Okay, and we can see if the same situation comes to the neighboring, means what I'm trying to say, if in degree becomes 0, so like what we have to do, simply post in our queue there. Okay, so like this is the basic intuition for this question there. Okay, and like this let's say if I'm explaining with the example there. Okay, so this is our 2 pointing to 3 pointing to 4 pointing to 1. Like there are the many of the, like how many of the edges is here, there is nothing but the 2 3 there, there is nothing but the 3 4 there. Okay, and there is nothing but the 4 1. Okay, there is the 4 edges. So one of the if I'm writing the one of the topological sort for this, so this is nothing but the 2 3 4 and 1. Okay, because now you have to see if this node 2 comma 3 2 and 3, so we have to see 2 comes before 3, 3 and 4, 3 comes before 4, 4 and 1, 4 comes before 1. Similarly, we have to see this in our previous video, so don't need to do this again in this video there. So like let's say this is our final resultant for this, and if I have to make the small dry run for this case, like I'm not doing the whole of the dry run for part this, because let's say see there is let's say I have the Q vector here, or we can say Q data structure I view. So we have to process all of the nodes here. So whoever the nodes whose has the in degree as a 0, we simply have to push this in our queue there. So we simply push this, and now reduce its neighboring in degree by 1. Okay, so its in degree initially as 1, but now becomes 0. Okay, so means we can now we can put this in our queue. Okay, so since we have to after pop this part and like add to our answer, now reduce its neighbor in degree, so that is nothing but the 4. So initially it has a 1, but now becomes 0, so that's why we have to add this part, so it becomes the 4. Similarly, process for the its neighboring, so initially it has a 1 in degree, now becomes the 0, so simply push this. Okay, so that is nothing but the our final order is as a 2 3 4 1. For this case, there is only one possible answer there, but like there are the many of the example where we have the multiple possible answers there. Like for this, there is a 2 3 4 5, or there is a 2 3 5 4, so both are the valid there. Okay, so that is of the code there. Now coming to the coding part, so we can like how to calculate the our in degree. So since our adjacency list is given to us, okay, so we know very well like how the adjacency list is giving is like we have given simply like there is a some key and there is a some value. Okay, so like it means there is a some node, and what are the elements it has in its neighboring, so these are stored in our vector there. Okay, so that means we can say here, so since it pointing to its vector there, so what are the element coming to the value, they has their in degree as this node is contributing to them. Okay, so now since this is a BFS version, first of all we are using the int v as a adjacent size, using the q initialization of q there, using our in degree vector there v comma 0. Okay, since there is a 3, so that means so of 3 size there. Okay, now coming to this part, for int u is equal to 0, u to v, u plus plus. Okay, so u is nothing but the like for traversing of u is nothing but the current node there. Okay, we have to traverse from 0 to v there, and now we have to see if we can say actually like this don't confuse with this is simply our adjacency list, this is our adjust list. Actually this code is of as of old version, so don't confuse it because in that manner it has to given our adjacency list manner there. Okay, So now we have to simply what we need to do, traverse for our edges. First of all, I have to traverse all over the adjacency list there. Now what we have to do, we simply go for all its neighbor and simply increase it in degree of all of the neighboring nodes there. Okay, so in degree of v plus plus there. Now we have to see in all among the nodes there, whosoever the in degree is 0, simply push in our Q data structure there. We are using the initialization of the resultant vector there. Now until our Q become empty there, first take that front element, simply push this in our answer, because what are the element, we simply push this in our answer and pop that element there. Okay, now since we have to pop this element, so since initially it has to contribute in degree of its neighboring element, so now after removing it means its neighboring element in degree also decreases. Okay, so what we can do, simply go to its neighboring part, in degree of neighboring is simply reduced by 1, and if their in degree become the 0, simply push this in our Q data structure, and like after it we can simply say there's the resultant vector is our the required vector then. Okay, and like was the time complexity and was the space complexity for this part. So this is nothing but the of we can say the v plus e part there, like why it is like, first of all I have to write this part there. Okay, so this is v for this part and it goes to its neighboring, so this neighboring is nothing but the, it shows me the edges there, so that's why it goes for v plus v. And like in the worst case we have to actually add up all of the q or elements in the all of the elements in q, so that's why it goes to the v element there. Okay, so that's mean basically your time complexity becomes O v plus e. So that's our question there. And like space complexity is because of the using this vector here and this q data structure here.